In this video, we're going to look at a single perceptron that I developed on a breadboard using analog electrical devices. We will power the circuit and train the perceptron on 2 input logic gates and see if it produces the correct output. We will see an hands-on approach in training a perceptron. There is no math or equation involved in this whole simulation. Before we go into the details of the circuit and start the simulation, let's have an overview on the biological neuron and compare that with the perceptron. I have a simple diagram of a biological neuron here and a comparison of a representation of a perceptron. A biological neuron actually has different parts. On the left, you see the cell body and the nucleus at the center. Attached to the cell body and the nucleus is the dendrites. Adjacent to that is a tail-like structure which is called axon, and at the end of this tail structure we see something called as synaptic terminals. A biological neuron fires and produces an output by receiving an influx of positive ions into the cell through these dendrites. Actually, these dendrites are connected to adjacent neurons. When the combined internal voltage reach a critical threshold, this neuron will start firing. And the firing actually happens on these synaptic terminals where the signals are transferred to the connected neurons. On the right, we have a representation of a perceptron. The perceptron has different parts as well. Here we see the input, the bias, these are weights, and this one is the bias. The bias, if you see, does not have an input to control, but bias and the weights are connected to the summation node. And next to the summation node is the activation function, and at the end we see an output. So the inputs are always binary, they're either 0 or 1. The values of the weights are adjustable or they are tunable. In the case of an electrical circuit, it's a potentiometer which can be tuned to different voltage outputs. The bias is adjustable as well, and it has no input control. However, it is always connected to the summation node. The activation function is something that determines the threshold value at which the perceptron should fire or not. Okay, what is a perceptron basically? It's a simple type of artificial neuron that is used in neural networks. They were inspired by the biological neurons, and perceptrons take multiple inputs and then they multiply these inputs with weights, and then they apply an activation function to produce an output. The important thing to note about a perceptron is that they can be trained by adjusting these weights. When multiple perceptrons are connected to form a network, they are called multi-layer perceptron, MLP in short. See, MLPs are the core component of a large language model like ChatGPT, Google Gemini, Meta's Ollama, and many other. Okay, why a breadboard perceptron and why simulate a logic gate? See, a breadboard circuit like this is to prove that perceptrons can be built in different forms. They can be on a breadboard. They can be built in a few minutes with little electrical knowledge. The perceptron that we will see today has 2 inputs and 1 output, and the idea is to imitate the functions of a digital logic gate. But the important thing to note is that we will not modify anything structurally to this circuit, and the system will remain the same. Just by changing the position of the potentiometer, we should be able to reproduce the truth table of a logic gate. The table that we see here are called the truth table for each one of these logic gates. There are 6 logic gates in this sheet, and based on the inputs on the A and B that are connected to these logic circuits or logic gates, we will see an output. So we should be able to simulate all of these within the same circuit. And another important thing that I should mention is that this is a single perceptron, and a single perceptron or a single layered perceptron cannot solve something called as a XOR logic and a XNOR logic. However, the multi-layer perceptron can solve this XOR XNOR problems, including many other complex problems. Okay, I will now go into the details of this breadboard components, and then I will start simulation. This is the breadboard, and it has two power rails. The plus 5 volt that is coming from the battery, that is this USB connection, and the black wire is connected to the ground. It has jumper wires, bunch of resistors, switches, LEDs, potentiometer, and an operational amplifier. The jumper wires help us connect the breadboard from one node to another, or from one component to another component terminals. The resistors are used to limit the current that is flowing through these electrical components. There are two switches here. I have a small switch here to represent. Here I connected positive 5 volt on one side of the switch, and the ground on the other side, so that when I switch off this switch, essentially I'm disconnecting both positive 5 volt as well as the ground from the circuit. And then we have two LEDs next to these switches. These LEDs will help us determine the status of these switches. When the switch is on, the LED should glow, and the switch is off, the LED should be power off. The first switch is switch A, and the second switch is switch B. These are the two inputs to this whole circuit. Switch A is connected to the potentiometer that is closer to me. I also have a small representation, a potentiometer representation with me. There are three terminals on this potentiometer. So these two terminals that you see closer to each other, they are connected to something called as a variable resistor inside this potentiometer. And the third terminal over here is connected to something called as a wiper. The wiper is the one that is adjustable. We can tune this potentiometer, and the wiper would touch this variable resistor, and by the position of the wiper on the variable resistor, we will get an output voltage. So we have three potentiometers. The potentiometer that is closer to me is connected to switch A. So we will call this potentiometer A, and the one that is on top of this potentiometer A is connected to the second switch, that is switch B. The third potentiometer that does not have a connection from the switch, or the one that is connected directly to the power supply, is the bias, and it is always connected to the summation node. In fact, all three potentiometers wiper outputs are connected together through this yellow jumper wires. So that acts as the summation node, and each of these potentiometers are 10 kilo ohms. The summation node is in turn connected to the operational amplifier. This operational amplifier helps us to or acts as a activation function in this whole circuit. The operational amplifier receives the input from the summation node, and then it amplifies this, the input over to on this output terminal. So this is LM2902. It has 4 operational amplifiers within this integrated circuit chip. I will attach the data sheet of this amplifier to on this video, and you will be able to see 4 individual op amps within this IC. We've used just one of them, and we've used pin 12, 13, and 14. Pin 12 is the input from the summation node to the operational amplifier, and pin 14 is the output to the LED. The LED is the one that will represent the output. If the LED is on, it means that this perceptron is firing. When the LED is off, the perceptron is not firing. In between pin 12 and 14, we have connected a few resistor, and we have configured this operational amplifier. in a way that it produces a non-inverting output. If you research about operational amplifiers and their configuration, you will understand what I'm saying. I think that's everything about the circuit that we need to know. Now let's start the simulation, and I'm going to start with the AND gate, the first gate. And I need to mention that it took me a few minutes or few hours and a lot of back and forth thoughts to achieve the correct potentiometer values. You see the potentiometer is the one that acts as the weights in our case. So it is a trial and error basis that we have to find the correct potentiometer setting or the position to achieve this AND gate or pretty much any of these gates. And that is how we train the Perceptron. In order to save time, I have noted down the voltage at the wiper outputs of each of these gates by training manually. And I have noted that down over here for each of these gates. And then I'm going to use that as the reference in this video to simulate or train this Perceptron. Okay, I will power on the circuit with this power supply, USB power supply, and to the right I have the digital multimeter. So I will connect the multimeters negative to the negative power supply, and I also have the positive terminal of this multimeter over here. So the first gate is AND gate. So AND gate should only produce an output when both inputs A and B are switched on. And to do that, I need to configure the potentiometer output voltage values to 0.28 volt, and bias should be at 0. I will connect the input terminal of this multimeter to the bias first, and then I will tune the bias to 0. Now you can see that the current potentiometer, bias potentiometer wiper output is at 0.18 volt. When I tune the potentiometer to the right, I'm going closer to 0 voltage. If I tune it to the left, I'm going to closer to plus 5 volt. So I'm going to turn it to the right as far as possible until the potentiometer value becomes 0. Okay, now it's 0. Now let me go on to potentiometer A and then set that to value 0.28. Right now it's this potentiometer is at 0 volt. See, this is one of the problems with a breadboard. Any vibration or little bit of shaking will destabilize the circuit and may produce an unexpected output. But it is easy to use a breadboard. You can pop in and pop out any of these components at your will, and you don't have to necessarily know how to solder and all the related issues with soldering. 0.28. Okay, that's 0.27. However, we need 0.28, but I think it is still good enough. It should work. Let me go over to the second potentiometer and tune that to 0.28 as well. 0.28. Okay. I think it should work, but let me give it a try. Okay, so let me switch off and go to off position on both inputs A and B. So there is no input from A and B, and there is no output. When there is input from A, I don't see an output. When there is an input from B, I still do not see an output. However, if I turn both these switches on, input A and B, I see an output. I'll do that again. No, input A and B are 0, and I don't see an output. Input A is on, and I don't see an output. Input B is on, I don't see an output. Both inputs are on, and I see an output. You may see that when I switch on input B, there's a slight glow on the LED. That is because the voltage at potentiometer B is at 0.3. If I tune it a little bit to the right and set it to 0.28, now you see that LED is no more glowing. Maybe you may not be able to see on the video, but through this angle from here, I'm able to see. I could see that little bit of a glow on this output LED. Okay, now this perceptron is configured to behave like an AND gate. I will quickly move on to the next logic gate that we have, that is OR gate. So OR gate should produce an output irrespective of input on A and B. I mean, either A and B is powered on, we should see an output, but if both the inputs are zero or switched off, we should not see an output. And the bias is still at zero. The wiper terminals on port A and B should be 0.55. I'll quickly check the bias voltage to see. Okay, it's at zero, and now I'll go to port A and then start tuning it to 0.55. 0.49, 0.555. It takes a little bit of time to settle sometimes, so I should stop tuning and then wait to see what value it settles down. So potentiometer B, I need to tune it to 0.55 as well. Okay, 0.54 should be also good enough, I think. Okay, I'll go to the rest position where both inputs are zero and I should not see an output. And any of these inputs powered on, I should see an output. Okay, I will switch on input A and I see an output. Input B, I see an output. When I power on input B, I see an output. And when both the inputs are on, I see an output. But when both the inputs are off, I don't see an output. So now this perceptron has learned to behave like an OR gate. So we have successfully moved from AND gate to OR gate. Basically, we trained or we taught the perceptron, to behave like an OR gate now. Next will be the NOT gate, or it is inverse of what it sees on its inputs. If inputs are 1, it should produce no output. When input is 0, it should produce an output. And to do this, I need to configure both the potentiometer A and B to 0 and the bias to 0.22 voltage level. So I will go with the potentiometer A and tune that to 0. I'm tuning it to the right and we can see the LED powering off, and okay, that's 0 on potentiometer A. Now I'll go to potentiometer B and start tuning this potentiometer. Okay, it's 0.01, which is closer to 0. I think that is sufficient. And now the bias should be 0.22. 0.22. I'm tuning it to the left. I think I went over 0.22, so I'm oops. That happens sometimes. 0.21. Oh, 0.22. It settled down at 0.22. I think now it should behave like an NOT gate. Let's go to the rest position. That's when both inputs are off. When both inputs are off, I should see an output, and I already see that happening. And if I switch on one of the input, my output should be off. And input B, when I switch it on, and I see the output in off state. And if I power on both inputs A and B, and I should see the output inverse, that is off. I think now this perceptron behaves like a NOT gate. We have trained that successfully to imitate a NOT gate. Next would be NAND gate and NOR gate. One important thing to see here is a NAND gate and AND gate are vice versa on their outputs. The outputs are inverse. Where you see 0 on the AND gate, you see 1, and where you see 1 on the AND gate, you see 0 on the NAND gate. And to perform this NAND gate, both inputs, both potentiometers, wiper terminals should be kept at 0 and the bias should be kept at 0.42. I think that is pretty easy to do, we have already tuned these potentiometer A and B to 0, but I'm just checking to make sure they are. And now I can quickly go on to the bias and tune it to 0.42. We're already at 0.22, so I have to tune a little bit to the left and I should reach 0.42. 0.42. That was quick. Okay, let's see if it behaves like a NAND gate. So a NAND gate should provide outputs when, okay, I should say it should not produce an output when both these inputs are switched on. So let's do that first. When both these inputs are switched on, it should not produce any output. So the last truth table is correct. The last row of the truth table is correct. But any one of these inputs are on, or if both inputs are off, I should see an output. I will try to keep switch A on and I see an output, and I will keep switch B on and I see an output. Now when I switch off both these inputs, I still should see an output. You see, all these three were tested and confirmed. So that's NAND gate the Perceptron was trying to perform. Now I will move on to NOR gate. So NOR gate should produce an output only when both the inputs are on off state, and the potentiometer terminals on the wiper terminals are 0, and I just have to tune the bias to 0.26 voltage. They are already at 0, the potentiometer A and B terminals on the wiper, and I am going to just tune this bias to 0.26. I don't know if you noticed, I went to 0.8, but last time I only tuned it to 0.4 on the NAND gate. These are the challenges with breadboards, folks. I think I have done that, but let me try to simulate the logic gate. So when both the inputs are 0, I should see an output, but that is not happening. So this is the problem. Something has gone wrong. Let me check the voltage level across each of these potentiometers. They are all at 0, 0. When I power on both these inputs and measure the voltage level at, you see, the bias potentiometer is at 0.18. However, we need that to be 0.26. I will tune this to 0.26. Oh, okay, I think now it works. So when there is no input on A and B, we should see an output, and that is what is happening now. No input on A and B, and I'm seeing an output. When I switch on A, I should not see an output, and when I switch on B, again I should not see an output, but I think I see a little bit of current flowing through potentiometer B, because I think it's not completely tuned to 0 voltages. And let me check again on the potentiometer. It's 0.27. I think that's good. Okay, I think that works better now. Let me do this over. So when there is no input from A and B, I should see an output. The first row is working, that's correct. And when I just power on input A, I should not see an output. And when I just power on input B, again I should not see an output. And when I power on both input A and B, again I should not see an output. You can see the truth table of a NOR gate, and it's working fine. You see, the buffer is the last gate, but it is very similar to OR gate. If you look at the truth table, the configuration is pretty much similar, so we do not have to simulate this once more. And buffer actually reproduces whatever sees in the input to the output. So that's a simple demonstration of how electrical perceptron on a breadboard works. When we connect this kind of a perceptron, when multiple perceptrons together, we can form multi-layer perceptron, and you know, train the perceptron to solve more complex problems. What are the inputs can we connect to this perceptron? What are the functions that we can train with this two input perceptron? Which other activation functions would you like to see simulated? Provide your thoughts in the comment section, and I'll meet you in another video. Thank you. Have a nice day.